Today, we add some more logic design aspect of job. So if you're a logic designer, you must know these very important things. If you're not, at least you get the idea what a logic designer does. The nowadays people thinks HDL programming like language. That's it. That's you write a code, then all the logic design is done. It's actually it's a very simplistic way to think. It's you still need a lot of timing issues to deal with. Okay. For example, when you ask a very junior designers to make a 4-bit counter, right? Then you have a flip-flop. You put the 4 of them, and you have a clock and the data. This goes maybe exclusive OR. So this is the control, and the counter is it's change 0101. Okay, and we put this one to the clock here, and put one to the clock here, and put one to the clock here. So it's a 4-bit counter with minimum hardware, and this works itself, but you never do this in the environment of large logic design. Why? The reason is this is a synchronous system. What is a synchronous? It's not synchronized by single logic. All the flip-flops not synchronized. Okay. If you want to make a synchronous, you have to do this, and same clock goes all the flip-flop, and say you have a control, and basically this plus 1 goes here, plus 1, and plus 1 goes here. So what you do is, ideally you have an incrementer. Is conceptually this 4-bit come in, and plus 1 other, just plus 1 other, and this is a 4-bit go back to this, right? And you may think, why you need an adder for just a counter? Well, it's just a plus 1, so it's going to be simple logic like AND. Go there, and AND goes, next one go here. So basically data is registered every clock at the same time, and the data is incrementing one by one. Okay, this is a synchronous. And for example, this guy, data in, change only when it's all 1, right? So only all 1, it's you add the 1 plus, then this guy change. This guy just waiting until everybody's line up to be 1 1 1. Okay, so you need a large AND gate and take all the input here and feed it to this guy, and only when all 1 line up, this guy get 1. Okay, so its data is processed in parallel with registers at the single shot of the clock. That's the synchronous system. This one, clock change, and this change propagate. So this clock and this clock is not synchronized. Okay, you use some asynchronous design for some design like a synchronous communication system. That's inevitable. You have to do it, but not this way. Okay, the LSI chip, you avoid any asynchronous part of the design on the chip because it's very hard to evaluate, see if it works or not on the chip. So what you do is, for example, some people do this. I'm gonna control the clock. This never do this. You know why? Because control may come from some here logic, and output of this logic may have many up and down until it's settled to some control state at the end. Okay, so if clock is high, in this case, during a high, those all it controls pulse. This is a transitional logic state, cause all the wrong clock into this flip-flop. So this never do this. This is very bad design. You never do this. Okay. Even there's no random logic. So this signal is clean, up or down. There's no intermediate transitional pulse included. Still not a good idea. The reason is synchronous design, the flip-flop, you have to care about four important timing, which is data setup time, T setup, and the hold time. And hold time you need minimum and maximum. Okay, and another one is this delay time, T Q out. So let me explain to you this detail. This is a rising edge flip-flop. If it's a falling edge, we put the circle here, right? So when clock goes up, data is getting into the flip-flop. The data has to be settling here before clock edge come. So this is the setup time. Okay, then the data can change immediately after rise of the clock? No, you can change the data after hold time. Certain period you have to keep data holding after rising edge of the clock, and this has a minimum and maximum, and the minimum sometimes become important. The maximum you have to hold it for maximum time, but actually you have to hold at least minimum time, yeah, and maximum time become important later. And after this data is in, output change. So clock edge to output, this is a TQ out. This is a delay time. Okay. So in the synchronous design, you have miscellaneous logic here, and critical path is defined this way. This miscellaneous logic signal goes through could be the sum of all the gate to delay time, right? And critical path is from this clock edge TQ out. It takes this much time to get the signal out, right? And here the clock come in, and before clock come in, this data input to the flip-flop has to settle. So you need another T setup time. So TQ out and T setup time, and plus intermediate logical delay time, it's all together should define the maximum clock rate. Okay. So this is the clock rate you define. Now there is sometimes the issue in this kind of design. If this Q go to D in immediately and the clock come in this case, this T Q out, right? When the clock come in, data change, but you cannot change too quick because there is a hold time. You need to hold the data, right? So this whole time, if TQ is too fast, then T hold. You cannot do this because you may get the wrong data in to this guy. Most of the time in design, TQ is slower than T hold time. But there is a T clock 1, T clock 2. They may have a timing skew. That means this guy goes up here, okay, and this guy slightly earlier. This is the T clock skew, okay. Then what happened is so many things happen. If it's earlier or later, you have to satisfy all this setup time, hold time, and stuff. And after TQ, this guy's output come out, right? If T is slightly here, then there is a setup time. It doesn't make it setup time. If there is a clock timing skew, it may violate the setup time or hold time. In this kind of, you want to have some kind of artificial delay, so you can insert some logic in order to make sure it satisfies all the condition. Okay, so you have this time, you have this kind of logic. You have to be careful when flip-flop output directly goes to the next flip-flop data. Make sure check hold time setup and think about the clock skew. Some percentage of clock is faster or slower, and if there is the chance for violating, this happened when clock signal driving many flip-flop, right? Then it doesn't become nice rise time. Sometimes it's become this kind of clock. Then you have all kind of problem, because the where you measure setup time and the hold time usually from center, right? But depend on the circuit characteristic, it could be a little bit higher or a little bit lower, and there is a certain clock timing skew here. So one clock drive only 3 gates, another clock drive 30 gate. The signal is going to be different. Look like this guy look like this guy looks like this. The clock skew get even worse. The clock timing skew get even worse. So that's why clock distribution has to be designed separately for the entire chip. The how many flip-flop in this module, how many flip-flop, and clock has to be generated for each module, and within the module it's too many flip-flop, it has to be divided. And if you have extra delay here, you need to have every clock need to have an extra delay. So clock has to be evenly distributed to the entire chip. Okay, so that's sensitive. When you're talking about very high speed, it become really critical issue, clock distribution. So that's common in a synchronous system. This kind of things you cannot handle in the HDL. So the logical designer has to pay attention to this. The asynchronous side, there is a logical design, like you have incoming data, and incoming data is usually come with preamble, regular clock, like a 20 clock, then data area, preamble. That's incoming signal, and your chip clock has to synchronize with this. How do you synchronize it? Okay, that's a typical way is you have a certain agreed speed, like 1 megabit per second. Then you prepare at least 20 megabit per second clock. So the clock going very fast up and down, and that is this single clock. And you capture this moment, transition moment between these two clock, right? And using a logic, you say, okay, I detected the clock, preamble clock edge. Once you detected preamble clock edge, okay, then you calculate this AND gate, your own clock and incoming clock. So it's going to be your own clock could be a little bit off, and frequency may be little bit off. So synchronization of this kind of situation is phase lock loop. Phase lock loop. What you do is basically you take an end, then there is some overlap here, and AND gate output goes to the diode, and low pass filter. So you get the voltage. And if phase look, the phase is off, voltage higher. If phase become very close, then voltage get less. So how do you control that? Your own chip clock generator is going to be voltage controlled frequency and clock. So your clock is running too fast here, then reduce the speed. The nominal is agreed 1 megahertz, but even same 1 megahertz, it could be 1.01 megahertz. The incoming could be 0.99 megahertz. So it's not synchronizing. In order to synchronize this completely, you have a voltage controlled oscillator, and that's the clock you use for your chip. And for incoming clock, you take an AND logic using after detecting this edge, you use the AND logic and get the low pass filter out to the to reflect that the difference in the phase to a DC voltage level. And this DC voltage level is going to change frequency, adjust your oscillator clock frequency. So it's kind of phase locked loop. This is a loop. It's after you detect this phase difference, you adjust the clock. Then within this preamble period, you can completely synchronize your clock with this guy. Then using this clock, you detect the data, receive the data. Okay, so this is kind of a asynchronous data transfer design. This is one of typical method to use. So this is completely logic hardware design, and when you cannot do this analog portion, then you have to digitize this. The digitize this get more complicated because you need to have a stepping delay time circuit. Means you can delay your oscillator's clock by certain amount, the stepping, and that stepping delay clock is often used in like a IC chip testers. Those Teradyne, those testers, they use a lot those circuit. And this is nowadays they don't use analog. It's use they use digitalized circuit, right? So there are a lot of things to do in the logic design. Sometimes asynchronous, you may need to use the analog circuit, but hopefully you keep entire chip synchronous design. Okay, so it's a clock distribution to this register setup, hold, and register delay time, clock to Q out. Those are very important parameters you have to know. And the critical path, TQ plus sum of all the gate delay plus the hold time. And this sum of gate delay, if this logic is complicated, it's very hard to see which one is the worst case path. And sometimes this software can help to identify which path is. This is like Google's map. In order to go to certain point from your point, the Google software search the shortest path, right? The same thing, because each leg of the road has a certain speed, and the combination of those, you can find the shortest path. And in this case, find the longest path, longest time it takes from here to here, and that's define the critical path. Critical path in the logic design. This is very important, and that's a way you can improve the clock rate for your chip design. Okay, so this is just additional some important key point in logic design, and there are lots of other stuff. Logic design. The logic design is not just looking at the logic diagram. They have to think many other things, which is not in the HDL programming code. Okay, so that's all for today. So please wait for next video, and if you like this video, please subscribe and hit like.